Well, let's have a look at the information on standing waves that we've been discussing. So here you can see an animation of a longitudinal standing wave in air molecules in a tube. And you can see that at the opening of the tube right here, the air molecules are going back and forth. They have the maximum amplitude. That means there's an antinode right here. And that means that you're going to have the allowed volume is going to be produced where this antinode is. Right here, the molecules are not moving at all. So this is a node. And the way that these longitudinal standing waves are drawn is with a transverse pattern right here. So here you can see that the amplitude is going back and forth like this, maximum, and that corresponds to this maximum amplitude here. And then we have nodes where the molecules are not moving. And then there's another node right here. And there's another antinode right here. So it's a convenient way of drawing longitudinal standing waves where you don't have to draw those dots because it's pretty much impossible. So that's just something to keep in mind. And here we have, when you put a tuning fork in front of a tube that's closed at one end, you can create a standing wave where there is an antinode at the mouth. So that means that the air molecules are going to be going back and forth here at the fastest rate, and that's going to generate a really loud sound. So as long as you have an antinode at the mouth, you get this resonance effect. The resonance effect is like a very loud noise. And if you look at the wavelengths here, like here's the length of the tube. So we just call that L. And the L corresponds to only 1/4 of a full wave, because this is a full wave right here. It's 1, 2, 3, 4 quarters. This is only one of the quarters. So the length of the tube would be 1/4 lambda. And when we rearrange and solve for lambda, it turns into this. Lambda is equal to 4L. We do the same thing here. Here the length is equal to 3/4 of a complete wavelength. 1, 2, 3. And when we solve for lambda, it turns into this. Down here we have 1, 2, 3, 4, 5 quarters. So the L is 5/4 lambda. And when we rearrange, it turns into this. So we can calculate the wavelength just by making this relationship here. You can see that this is going to be 1, 2, 3, 4, 5, 6, 7 quarters. And then when you rearrange for lambda, you get, this is, if it was for this one, it would be 4/7. But they just keep going up and keep going up and keep going up. Now here are tubes that are open at both ends, which means that you will have antinodes at both ends. And each time they're going up by half wavelengths. If that's the length of the tube, which is open at both ends, the length here only corresponds to half a wavelength. But when we rearrange, when you cross multiply, the lambda is double the length of the tube. Here we have 1, 2, 3, 4 quarters of a wave. That's one full wavelength. And here we have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 quarters. 6 quarters is 3/2. And then when you rearrange, you get this. And the other thing to remember is when the tubes are open at both ends, the harmonics go up and the frequencies go up in integer multiples of each other, because the wavelength is going down, right? So here the wavelength is halving, so the frequency has to double. If the wavelength is down by a factor of a third, the frequency has to go up by a factor of 3 in order to maintain the equal wave speed. So here are some questions. There's a column that's closed at one end, and it is 20 centimeters long, and the fundamental frequency standing wave is in there. That means that there's the first antinode is at the surface. So it's generating a very, very loud noise like that. And this is 0.20 meters. And right away, I can see that the lambda must be 4 times the length of the tube, which is 0.80 meters. And so now here we're given the speed of sound, and we want to know what is the frequency of this standing wave here in part A. Well, we use the universal wave equation, and when you rearrange it, frequency is v over lambda, which is 350 over 0.80. And then solving that, it's 437.5. So 438 hertz. And now we want to know what's the frequency and wavelength of the third harmonic. So the third harmonic is the next antinode at the surface. It's still 0.20 meters, the length of the tube. But now we have a different frequency creating this resonance effect. Well, right away I can see that the length of my tube is equal to 4. That's not right. 1, 2. Oh, I have this drawn wrong. 1 second. Nice try. So it's got to go like that and then down this way. There we go. So now I've got it drawn right. So there's 1, 2, 3 quarters. Nice. So the length is 3/4 lambda, and lambda is going to be 4/3 L. And it's still 0.20 meters. Had to have a node here, which is, I had it drawn incorrectly, and an antinode at the surface. So now that means that the wavelength is 4/3 of 0.20. So my wavelength, 4 divided by 3 equals times 0.2, 0.267. And now I can calculate the new frequency. So here the frequency is again 350 over 0.267, which is 1310 hertz. Now, the wavelength dropped by a factor of 3. So guess what? The frequency went up. So this is, the 1310 is 3 times 438. So here the wavelength dropped by a factor of 3. Right? There's 1/4, 3/4. So that means that the frequency had to go up by a factor of 3. 438 times 3, it's going to be 1310, or close enough when you round it off. An open air column is vibrating in the fourth harmonic with a frequency of 120 hertz. What's the fundamental frequency? Well, now this is open at both ends. So we have antinodes here and antinodes here. And we're told that the fourth harmonic is 120 hertz. So what's the fundamental? Well, let's just go back a couple pages. So you can see here that the fourth harmonic is 4 times the fundamental. This is the fundamental here. The first harmonic is the fundamental frequency. And there's the fourth harmonic, which is 4 times F1. So if the fourth harmonic is 120 hertz, the first harmonic must be 120 divided by 4, which is 30 hertz. That's the ratio. If you know the fundamental, then the fourth harmonic will be 4 times the fundamental. If the speed of sound is 344, what's the length of the air column? Well, I can find out. So let's draw this now with the fundamental in there. So when it's open at both ends, it's going to look like this. There's an antinode at both ends. There's my L. I know that my wavelength is 2L because look, there's a quarter, there's a quarter. So that means that the L is 1/2 lambda. And when we rearrange and solve it for lambda, we get, oh, lambda is 2L. It's double this. So now I can find out so like I have the frequency is 30 hertz. I have the speed of sound is 344. And if I'm looking for the L, I know that the universal wave equation says this. V is equal to lambda F. The V is 344. The lambda is 2L. Whatever the length of this column is, you would have to double it to get lambda. And then you multiply that by the F, which is 30. So that means that the L is going to be 344 all over 2 times 30. And this works out to be 344 divided by 2 times 30 equals 5.73 meters. And that one is done. On to the next one. An open mouth vertical tube is filled with water. And we're told that this length is 0.240 meters. This is 1/4 wavelength. So remember, if your L is equal to 1/4 lambda, your lambda is equal to 4L. So that means that the lambda is 4 times 0.240, which is 0.960 meters. And I'm told that the temperature is 20 degrees Celsius. That gives me the speed of sound. And remember from the equation that when you put in 331 plus 20 times 0.6, you get 343 meters per second. So now I can find out the F is equal to V over lambda because it's just the rearranged version of the universal wave equation. The V is 343. The lambda is 0.960. And it's 357. At what length will the second resonance be heard? Well, it's the same tuning fork. So there's a 357 tuning fork producing this resonance. So it's the same tuning fork, which is 357 hertz. But now we've gone from the first antinode to the second antinode here. This piece must be 240, right? Because it's a quarter wave. This has got to be 240, and this has got to be 240. So the length of the tube that would produce the second resonance would be 3 times 240. 3/4 of a wavelength. 3 times 0.240. And it's 72, 0.720 meters. Tricky stuff. We have one more. A tuning fork is placed over an 85 centimeter long tube. So 0.850 meters. We've got some kind of frequency here from the tuning fork, which we do not know. And the wavelength here, so 1, 2, 3, 4, 4/5 of this length. So 4/5 of 0.850 corresponds to a complete wave. 1, 2, 3, 4/5 of the complete length. That's going to be our wavelength. So 4 divided by 5 equals times 0.85, and we get 0.680. And now that we have the speed of sound, we can calculate the frequency of the tuning fork, which is V over lambda, 340, over 0.680, and that's 500 hertz. And now we want to know the length of the first resonance. Well, it's this length here. That's going to give us, so this is a 500 hertz tuning fork, and a column this long will produce a resonance because it's where we hit, and a column this long will produce a resonance, and then the next one occurs here. Right? So wherever you see an antinode, you will get a resonance. So the length of the first resonance is 1, 2, 3, 4, 5. It is 1/5 of 0.850. That's the length that will produce the first resonance. There are 1, 2, 3, 4, 5 quarter wavelengths here. So 1/5 of that entire length will do the trick. So 0.85 divided by 5 is 0.170. In other words, 17 centimeters will give you a resonance in that case. And those are all of the examples.